and solve them. This is classical poroelasticity. Sometimes called Biot's equations. Even though he never wrote them just like that. They're the same, is what he wrote down. It just, he never wrote them, presented them in this exact form. All right, so again, this is our goal now for the rest of class, is to learn the computational techniques it takes to solve those equations. Because, can anyone solve those by hand? No. Can only, all interesting problems. The only problems left, all the problems that can be solved by hand have already been solved by hand. The only problems that we have left that are interesting are problems you have to solve with a computer. So that's what we're going to learn now. And so, yeah, we won't see these equations again for a bit because we're going to have to work out the finite element technology. What we're going to see, and a lot of people, especially in petroleum engineering, don't solve these equations correctly. You remember when we introduced P when we first introduced it, what was it called? I called it a pressure later, but what was it first called? Huh? No. It was, I just said it earlier in the class. Lagrange multiplier, right? All right. If you remember, I don't know if I said it, but in the application of Hamilton's principle, you might look at that problem or think that it's a minimization problem, because remember we talked about in the variational methods, right? You have this arbitrary function that varies, and basically then you minimize all combinations of them, and it's like the actual motion in the body is the one that's such that minimizes the energy. And we talked about that, like principle of least action, right? Like that's how everything in nature evolves. Okay. Problem is when you stick that Lagrange multiplier in there, what you get is actually not a minimum. You get a saddle point problem. So nothing incorrect about what we did. It's just the equations that we arrived at are not at a minimum. They're at a saddle point. You know what that is? It's like an inflection point where, where the second derivative is 0, and so it's not a minimum. It sits at an inflection point, and saddle point problems are always computationally tricky, right? Because if you know anything about optimization, or nowadays we often think about problems in the context of machine learning. By the way, machine learning is just optimization, right? Like if you know anything about machine learning, you often train a neural network by gradient descent. Well, like gradient descent, what does that mean? You have some objective surface and you're just descending, right? Trying to find that minimum. But when you have a saddle point, it's like there, and if you move a little bit in each direction, right? If you don't converge there, if you just move a little bit in this direction, you're going to go to some other minimum over here, or just diverge completely, right? So saddle point problems are always tricky to solve. And in the context of finite elements, though, we have a theory that lets us know when or know if this formulation is stable or not. Okay, it's called the Imp-Soup condition, or also known as the Babushka-Bregy condition. Right? Babushka was a guy that was here at UT. He passed away last year. He was like 2 years ago. He was like 95 years old. And it's probably that result was in like 1974, probably one of the most celebrated results in finite element analysis. But the point is, and we're going to talk about it briefly in the class, but basically what the context of like, and the reason I teach you in terms of finite elements is because finite elements has a rigorous mathematical theory behind it that can allow us to basically determine when when the numerical solution to this set of equations will be stable or not. And I can tell you that most people in petroleum engineering don't solve this in a stable way, because almost all like reservoir simulators, geomechanics is an afterthought, right? When you use CMG, geomechanics is like an extra module, right? And so the built-in discretization in CMG is like a finite volume discretization, right? Well, when you solve these equations using a finite volume discretization, you result in, and I'll prove it to you later in the class, you end up in a system of equations that's unstable. It violates the inf sup condition. Now, you don't always see it, but when you do see it, you'll know it, because basically you get this checkerboard pattern in pressure. Like literally, well, we'll prove it. You'll see it. You get an oscillating pressure field due to the instability in the solution scheme. Now, you don't always see it because typically it only arises in really low permeability settings. And so, I'm not saying that every computation that you've ever seen in CMG with geomechanics turned on is wrong. I'm not saying that. But the formulation is unstable, and I don't know how you could ever trust an unstable formulation. Now, it just so happens that pressure oscillation is very obvious when it appears. Like you see it, and you're like, oh gosh, this is not right. But sometimes instabilities aren't that obvious. And me personally, I'm never going to trust a numerical method that I know has some built-in instability, because you can't, if you have a lot of nonlinearities and stuff, you can't always know if what you're seeing is the truth or just some unstable result, right? So we'll talk about all that when we go forward, and that's the reason I like to teach this in the context of finite elements, because it gives us the variational theory to basically prove the stability. And then once we prove the stability, I can show you how to fix it. I can show you an element formulation or an element technology that is stable always, and then we can solve the equations that way. So your final project will be a problem where